To see Will and Dan's amazing presentation on miniKanren earlier this afternoon. So this talk is not going to be about how to use miniKanren. This talk is going to be about how it works. miniKanren is great. It's actually quite an old system. It's been around since 2004 in some version. core.logic is about 2 years old now, and I hope by talking about a little bit more about the internals that people might get excited about contributing some more to the project. I think currently it's a bit like Warren's abstract machine. It's sort of like a mythical thing that people are like, I can never understand how that works. I think this talk is an attempt to remove some of the mystery. So, miniKanren is well described. One version of it is well described in this book called The Reason Schemer. We're particularly lucky at Strange Loop this year because we have all the authors at one conference. You should ask them questions. So what I want to do here is, this is a pretty implementation detail specific thing. So if something I say is confusing, raise your hand and I'll try to answer it fairly quickly. I do have a bunch of slides, but I don't mind slowing down if something isn't clear.
It's too loud.
Is it too loud? Is this better? Is this better?
Yeah.
Okay, great. All right.
Are your slides up already?
They're not. I will. I'll update them. So in 2004, Oleg and Dan sort of collaborated on a system called Kanren, which was an attempt to sort of get Prolog semantics into Scheme in a nice, clean way. And it was a fairly large system. It was actually quite fast. They benchmarked it against Sweet Prolog, and it was pretty surprising that they were able to, really get the semantics of Prolog and be able to compete with a code base that's largely written in C. So what was nice about that is that the Kanren system was cool in terms of proving that it could be done, but it was a very large system. And Will, Dan, and Oleg, they collaborated to really just absolutely get it down to its barest essentials. And that's what's sort of discussed in the Reason Schema. It's kind of like, you sort of read the book, it's a very difficult book, it's a very short book, and you sort of are just completely baffled, and then you see the last 2 pages, and it's like, oh, this is 4 pages of code, and you're like, wow, I really need to understand how these 4 pages of code work. Because it seems that a system that seems so sophisticated should require lots of code. So, just a quick review. So this is, again, I'm not going to show you how to use it. We're going to break down how it works. So this is a standard expression in miniKanren with slight changes here because this is Clojure. But run star, we have a logic variable Q, and we're saying a goal here. We want to unify Q with true, and I'm sort of outputting what the result would look like. So the first thing, whenever you see this, you know that you're not in the normal functional programming realm. I mean, it's a bit of a sleight of hand. You actually are still doing functional programming, and we'll see how that works. But know that the operation of the program is going to be quite different once you enter run star. You can immediately identify what's going on because Q is the logic variable. We'll talk a little bit more about how they work. And this expression where we say unify, this is not a comparison operator, though it can sort of double as that. It's a goal, it's a relation, and we construct these things when we write miniKanren programs. So goals, this is why I was saying really it's a bit of a sleight of hand because goals are just functions. In fact, unify is actually just a function that takes the 2 arguments that you saw and it returns a closure. It closes over its arguments. And really, there's this weird magic mystery thing. What is that argument that it takes? And we're going to sort of dissect what that mystery argument is. So these are the results. miniKanren always returns multiple results. It's very much, people get confused by this, but it's exactly like SQL, right? You get a result set. And in a similar way, miniKanren returns a result set. So here, there's only one possible value for Q, which could satisfy this program. We're basically trying to say, for what value of Q is this program satisfiable? And Q is our escape from New York, right? It's the way that we start this crazy thing, this process, and Q is the way we extract that value out of that process. It's important to note that we can flip, right? This unify goal, it doesn't really matter which way we pass in the arguments. And this is why this is a bit of a curious thing. It also, you'll note that when you write something like this is a program that has no possible answer, right? It's not possible for Q to be true and to make a statement, a logical statement like that, and then for it also to be false, right? It's not, you can't satisfy that, so there are no results. And it doesn't matter which order. But the thing, something that helped me early on when I was getting into miniKanren was to sort of think of logic variables as what are called single assignment variables. So just, we'll see what it really is, but you can sort of think, oh, we sort of assign Q to true, and we're not allowed to reassign, right? You're allowed to see, is it that value once you've assigned it, but you really can't change it. That's why this fails. And it doesn't matter. Once you see that it's a single assignment thing, right, it doesn't matter the order. Once you have a conflicting assignment after the first time, you're going to have a failed miniKanren program. And that's why this works, right? We assign it to true to Q, and we're allowed to assign it to a similar value, or this exact same value, and that's going to work out. So single assignment, this is a big idea. You can read quite a bit about it if you look at the Prolog literature, but also there's a pretty cool language called Mozart-Oz that sort of talks about this a lot.
Called what, sorry?
Mozart-Oz. So here's a more complex expression. Yet again, it seems like I'm introducing something new. It's fresh. Don't be scared. It's exactly like schemes let. It delimits a lexical scope. It introduces logic variables. So until we saw it, really the only way to do that was run. Like run provides that one logic variable we can use, but fresh allows us to introduce as many as we want. And unlike scheme, you don't actually bind those locals to values, right? Fresh creates a lexical scope, you create logic variables, but you really have to use unification to associate logic bars with values. So this is kind of fun because if we look at this, what are we saying? We create some two logic variables. We have a Clojure vector, and we say, how can we figure out a vector which has 1 and y, and a vector x and 2? Is it possible to make these terms equal? And we use Q because we want to get out of that world and see which values for y and x that this works out. And so it turns out that, yes, if x is 1, right, and y is 2, that first line, that first unification works out. And when you sort of get this, I mean, you kind of feel like this. It seems like a little bit magical, right? Like the whole unification and how much power you can get out of that process. So unification, it's an attempt to find the solution that will make the two terms equal. Trivial cases, you can unify 1 with 1, and that's trivially true. It's trivially false that 1 and 2 cannot be made equal. But as the previous slide, go ahead.
Do you do unification in the Clojure destruction stuff too?
We do. There is support for that. I'm not going to talk about it, but that's just sugar. It's just sugar over the more basic thing. But we can also do complex terms, as we saw in the previous slide. And when I say term, just think S expression, right? That's all I'm talking about. We're using lists, so terms in our case are just S expressions. So unification. So what is actually happening behind the scenes? We have to have a map-like structure, right? It shows which bindings logic variables we're going to have. We want to minimize bookkeeping. So if we're going to do this, we want to absolutely minimize bookkeeping if we have to backtrack. And this is because if you think about Prolog, what does Prolog let you do? If it doesn't find an answer, it sort of rewinds, right? And then tries a different branch of the search. So we need some kind of persistent data structure. And it turns out, well, this is a really great data structure for backtracking, basically backtracking for free, right? Thank you, John McCarthy, for really getting us to think that lists are truly a powerful and useful data structure, and they are naturally persistent, right? So triangular substitution is the big idea in the way that miniKanren does substitutions. So a substitution map is a list S. You'll see this in the source code, and it's a list of 2-element tuples, right? In each tuple, variables always appear on the left-hand side. It's not possible for a value to appear on the left-hand side. So it's very map-like. Lookup is a linear traversal over the list that examines the left-hand side, trying to find a match. So what are we going to do when we look up the value of the logic variable? We're just going to traverse the list looking for the variable that matches, and then we can grab that value. So here's an example substitution, and this is what it looks like. So if we want to look up the value of x, what do we have to do? We have to go through the head of the list, keep going. We're going to see x is bound to y. And we start all the way over, and then we're going to go through the list, and we see that y is bound to z, right? And then we start again, and we found, oh, z's right there, right? X is bound to true. This is how the substitution map is represented in miniKanren. And just a little bit more examples, a few more examples. So here, in that initial example that I showed you, it's just a substitution map that has q bound to true. In this case, right, let's just break it down. After the first goal is run, the substitution map looks like this. You've got x and y. In the next step, you've got y is bound to q and x is bound to y. And the last step, well, that's kind of weird. What happened? Why is q bound to true? And this is not as strange as it seems. What's going to actually happen before unification gets to run? We have this expression. Let's bind x to 1. What's going to happen if the substitution map looks like this? We're going to first say, well, really we need to look at y. We really need to look at x is y. Then y is q. Now that we've found the true value of that logic variable, now we can run the unification. This is the actual binding we want to add to our substitution map. So this process is called walk. There's a function inside of core.logic and miniKanren called walk. It's called walk, right? Yeah. So what's a little bit different in core.logic is that in miniKanren they actually can just use lists. It works out fine. Because there's some other things we want to do in core.logic. In particular, we have constraints. So we sort of have a package. We have this notion of a package, something that wraps up a bunch of other fields. But the very first field in substitution, this is a type, a package, is S. And in this case, we don't actually use lists, because if you sort of thought about it, well, what if that substitution map gets long? We have to keep traversing the list, right? We can't just look up a variable in one step. So I changed this and went ahead and used persistent hash maps, because they have the same property as lists, in that they're naturally persistent. We still have simple backtracking, but we don't have to pay that cost for looking up variables. So in the substitutions type inside of core.logic, we have a persistent hash map instead of a list. So this looks a little bit strange, but this is because this is a method inside of our type. So we don't have to say this is a function. This is a sort of method on substitutions. And what does this do, right? This, in this case, represents the substitutions instance. And what we want to do is we want to find inside of S, what is the value of V? V could be anything. We could be looking up 1, we could be looking up a variable. We're going to go through the cases, right? So, sorry, that was actually a mistake slide. This is fixed. We're going to find in that hash map, right, what it is. But before we go to the next line, when we say find SV, what's happening when we say V is going to be the key, VP is the value, and ME is the map entry. So either we found something in the store, or we didn't in the substitution map. So in this case, we didn't find it. There was no binding for V. And then we just return whatever we found, whatever we were given. So 1, you look it up in the substitution map, you're just going to get 1 back. If it's not an LVAR, then we succeeded in finding the value that the LVAR was bound to. If we have a variable, we have to keep looking. This is exactly the process that I described in these sort of drawings. Did somebody raise their hand? No? Okay. So we sort of have a sense of how we store values in the substitution map. Now we can sort of have enough information to break down unify. So if we look at the implementation of unify in core.logic, we have some parameters. We have S, which is the substitution map, and we have U and V, which are the terms, right? First thing we check, are they identical, right? We don't need to unify. If we see that 1 is 1, right, there's no work to do. We don't need to do any computation. So what we do is you see we return the substitution map immediately, right? So you can see that some things don't extend the substitution list, right? There's nothing to add. If they aren't identical, then what do? We walk them. We already know what that does, right? It's going to give us back, what that value really is if we were given bars. And then we do another slight little optimization here. We just check, are they identical now, right? If they aren't, if they are, then just return the substitution. If they aren't, we need to do more work. We actually have to attempt to unify the two terms. So core.logic and miniKanren are slightly different in the way they deal with unify. So miniKanren only really deals with scheme types because that's all it needs to. List is the only type that triggers any recursion during unification. Clojure has more data types, maps, sets, and vectors. And this means that people are going to want to unify these types. So unification needs to be polymorphic, and it needs to be open. To be honest, when I originally did this, I was just doing it for performance reasons. And then later I was like, oh, this is actually kind of useful. That unification is now open to a larger set of data types, and people can extend the system however they need to. But originally this was just a performance optimization. Because this is the code. And this code is fine, but we have a very large conditional. And I was hoping that the JVM could optimize, do some optimization if I eliminated the conditionals and just had polymorphic calls. But if you look, I really stayed true to what goes on in Unify, right? They walk, they first check, are those things identical? Is it a var? Then they go ahead and extend the substitution. Is V a var? Extend the substitution. Again, now if we have pairs, if both U and V are pairs, meaning are they lists, we do a sort of recursive thing. We need to unify each element in the list, right? Otherwise, if they fail, they return this value false. Core.logic is different here because we just return nil. So now we can sort of break this down, right? So unify, if we look back at this goal, we can imagine, early on I think miniKanren, the unify operator was a macro at one point. Was it? Yeah, you went back and forth. So let's pretend it doesn't have to be a macro, it can be a function, but let's imagine it expands to this, right? It expands into, like I said, a Clojure, right? And it's going to unify Q and true, and this mysterious A, this mysterious argument that I talked about, it's actually our friend. It's just the substitution, right? It's all goals simply take the substitution map and they either extend it, they return nil, or they return it unchanged. That's literally, all there is to it, to the nature of goals. So Q and true are those terms that I was talking about. So we can sort of start breaking this down. So this is, in core.logic, unification is polymorphic, and I have a couple of tricks in here to make this work. So I make a protocol called iUnify_terms, and what we do is U and V are the terms, and S is the substitution, and just so that this part is easier to understand, I'm going to just describe protocols and how they work. All they do is create polymorphic functions that dispatch in the type of the first argument. You can extend types to a protocol even if its original implementation did not implement it. You can actually do special handling at nil, and this is kind of nice, and we'll see why. We can also define default implementations by extending a protocol to object, and we'll also see why this is useful. So let's look at logic vars. Logic vars are actually represented as a type. In miniKanren, they just use vectors, but right, vectors, right? So in core.logic, we actually have a type. And we look at the implementation for unified terms for LVARs. And what does that look like? All we do here, right? The magic of open unification is we now know that we're inside of the LVAR, right? The LVAR is unifying with some other term. So we simply dispatch on unify with LVAR, and we flip the argument so we can figure out what the other term is, right? So all the unification, it always happens that somebody implements iUnify terms, they know their own type, they now dispatch on the other argument saying unify with me, right? So you have to implement unification with me now. And here it is, right? So object, right? So some other term can do this. I can unify with LVAR, and what do? okay, you're the LVAR, I'll extend the substitution with you, right? With the LVAR that called us. And again, that's enough information to understand what happens in this case, right? Well, actually, in this is simple because this won't even, those are identical, so nothing will happen. But let's imagine, actually, there's not a good example for what I want to show. But let's break this down. These are all the cases for ununified term, right? What happens if you unify with nil? What happens in the default case, that's object? And then we have the recursive cases down below. So if we unify with object, what does I unify with object look like? Now this is the default cases, right? This handles everything else. And again, you can see if the object was identified, and now we want to unify with the other thing, and it also is the default case, all we check to see is, are they equal, right? Are they equal? If they're equal, return the substitution map unchanged, and return nil if you fail. So whenever you see nil, it means that we failed somehow. It couldn't be done. We couldn't unify. And again, these are the recursive cases. I'm not going to spend too much time on them because they look exactly the same as the list cases in miniKanren for Scheme. We just go through these sequential-like things and unify each one of the values they have. Again, vectors, lists, lazy sequences, they can all be unified with this case. So let's talk about escaping from New York, the process of how we extract values out of the system. And this is called reification. So here's a program, right? What do? We say unify x with 1, unify y with 2, and then we unify q with a vector with x and y. And we get back 1 and 2. Though this should cause some confusion. Why is it the case that we don't see just the logic bars, right? Something magical has to happen for us to have not seen this, right? We know what the substitution map looks like conceptually, right? It's going to be a list that looks like this, right? The first thing we did was unify x with 1. The second thing we did was unify y with 2. And then we unified q with x and y. We already saw walk. Why doesn't walk return that value immediately, right? Just the logic bars. So we saw the code. Walk is not recursive on its values. It doesn't do that. It doesn't need to do that. So there's a special thing called walk star, which actually completely walks its value. So not only does it walk once, but if we have a list or a vector, we're actually going to go ahead and go through the whole thing and walk all the values inside that thing. So walk star looks like this. Walk star takes a substitution, takes some value, we walk it, and then we walk term. And again, walk term is polymorphic, and this allows people to do whatever they need to do, though I've handled most of the cases that are interesting already. And again, it's a protocol. So, in this... Oh, so what happens? So this is something you see a lot. So when Will and Dan showed their code, you often see these these vars that were never bound, right? Fesh vars. They have this special, nice little naming convention. Like this thing never got bound to anything, right? Q has no binding, and we get this underscore dot zero. How does that work, right? So here are 3 functions that are critical. When we reify a value, what are we going to do? First, we walk star it, right? And then we actually do this thing where we say reify star empty s. Empty s is just a new substitution that's empty. And all they're going to do here is they're going to stick the mapping from that var to its new name before we actually show it to the user. And that's all that does, right? Again, this is yet another polymorphic function, just so if we need to do something different for different types, we can. And here we can see an LVAR, right? When we reify an LVAR, this is an LVAR that was never bound to anything. What does it do? It extends that empty substitution with that underscore name. So however many logic vars that were unbound, that's going to be its name. So if there's only 1, it's underscore dot 0. If there's 2, underscore dot 0, underscore dot 1. That's actually, were there any questions about that before we go into this next part? Yes? Go ahead.
Why were the unified variables invented?
Which ones?
The underscore dot 0.
I I mean, it's something that does exist in Prolog, right? Not quite the same way.
I'll tell you this.
Go ahead.
We initially were using a symbol that was associated with a variable like codex. And then if you pass the arguments to unify flipped, you don't get the same answer. Okay? You just don't get the same answer because you might have a variable that was made with x here and a variable that was made with y here. And then you flip it, then they're going to be flipped. So you don't always get the same answer. So we wanted this theorem, well, sort of like a theorem that said you really can flip them anytime, anywhere, no risk. And that's why it was invented.
So you actually can't do the thing you do in Prolog, because Prolog will give you different answers.
That's right, it gives you different answers. Yeah, we don't want the different answers.
Cool.
Prolog answers are usually like gen-semi, and they have numbers that are unique and stuff like that.
So this is actually, hopefully, you didn't think the first part was the hard part. This is where it gets hard.
Well, one thing you didn't mention with unification was the occurs check.
Yeah, I didn't talk. So it is possible in Prolog to run into trouble if, for example, you try to unify X with a list that contains X in it. So when we extend the substitution, we do a check to make sure that that value doesn't exist inside of itself. It's called the occurs check. I don't talk about it because it turns out that for many Prolog programs, you don't need it, but it is important.
Is that interesting at all when you go to the applied market model of unification? Do you have to
we have a special, yeah, we do something with the current, like, I mean, I should have at least put that slide in there, but we do something for that. Yeah. So this is the hard part of the talk. This is the part of the talk where, like, you know, you get through, I read William Byrd's fantastic thesis, which I recommend. All of miniKanren is basically described in chapter 3. And it's actually a good read, especially if you've already seen this talk. But I remember the goals section, I think I read it like 8 times, and it still didn't make any sense until I actually went ahead and implemented it. So hopefully, this might make, you won't have to read as many times as me.
You put a warning sign, magic here.
Yes. So when you talk about goals take a very specific kind of value. I sort of glossed it over by saying it takes a substitution map. But what goals really conceptually take is something that they refer to as A infinity. And there are basically 4 possible cases for this type, right? It can either be nil, and I'm not going to talk about monads, but that's M0. It could be substitution, which is unit. It could be a choice, which I've never mentioned this at all. Or a thumb, which I also haven't really talked about yet. So just keep this in your mind. There are absolutely 4 cases, and we need to address them all. So I want to talk about something called bind. So I'm going to sort of remove some of the magic here. Now, what I'm going to show you is not what the macro actually does. Again, this is just an conceptual illustration so that hopefully you can form a mental model of what happens. So what run star is going to do is sort of going to move those goals around and do something slightly magical. So first, let's imagine a first fake macro expand, and those unifies expand out into their closures, right? Then run star is going to change those, and it's going to actually insert these binds. And what does it do? It's going to take an MC substitution. It's going to apply it, right? It's going to apply it to that first goal. It's going to get some value back, and then the outer bind is going to apply that to the next goal, right? So what happens in the first thing, right? We're going to get a substitution map where Q is bound to true. After we apply the next goal, it's just another statement, right? Q is bound to true, so we still have this. And then the reification process will look in there and pull out true. So what happens in this case, right? We have conflicting goals, and this is going to return no solutions. But we can see that we're going to have a substitution map after the first goal that looks like this. Then bind is going to apply that value to that function, and we're going to get nil because that goal is going to fail. It's not possible to unify true and false. And we know how that works because we saw unification, we saw walking, right? It's going to walk Q. Q is going to return true as its value. You're going to attempt to unify true and false, and that's going to fail, right? So this is why we don't get anything out of failed goals. So again, another polymorphic function. It's called bind. The protocol is called iBind, and everybody, all the interesting types that I mentioned, nil, substitutions, choice, and functions have to implement this. So it takes two arguments. It takes a infinity, and it takes the goal. So what does it look like for substitutions? Right? I said it was just function application. That's all it is, right? We take the G, and we call the G with ourselves, because we are the substitution. That's all that it does. We have to handle nil. What do we do when we get a nil? We're done. There's nothing to do. We just return nil, right? It's over. We failed. We're just going to cascade the nil. I just want to finish this section by showing a slightly different example. We're going to get a little bit more abstract because I don't need to show concrete goals. So we can imagine some goal 0 and some goal G1, and we have a fresh. And I just want to show you that fresh does the exact same thing to its list of goals that conceptually what run does, right? So you can imagine what actually happens is that I said fresh is like let. It actually expands out into a let, right? There's a let, and we have some constructor functions that create the logic bars, right? So that the goals can see them, right? And do their thing. And so what are we going to do? We're going to bind MTS to that goal. We're going to get something back, and then we're going to bind that value to the next goal. The trick is, now I'm going to show you, reification gets magically inserted. You know that when we extract the value, it's a magic goal that's inserted by run, right? So it's the last step. It's always the last step. It's a real goal, and it's going to look up the value of Q in the final A and pull its value right out. So this is where it gets maybe a little bit harder. So up to now, everything was simple, and it was simple because we only used fresh and we only used run, and those are they basically use their goals as conjunctions, as conjunctive statements. So there's always only one possibility. But the moment that really when it gets interesting when you use cond E, because cond E creates the possibility for search for multiple possibilities. So here's a program that's similar to something you'd find in the reason schemer, where we say Q is either tea or coffee. I mean, that's semantically what this program means, and we're going to get that result. So it's pretty intense what a cond E expands into, whereas front star and fresh are a bit simple. Cond E is pretty crazy. So what here we say, we're going to bind the MTS, and the cond E expands out to the lower part. It's a goal. Cond E is also a goal, right? And the body expands out into a series of M pluses. If we had more goals, there would be more M pluses. But here we only have 2. So what do we do? Just to review the way that miniKanren works, so you have ors, like cond E is like or, but the actual line is ands, right? We have an implicit conjunction in the particular line, right? I could have multiple goals in that line.
So within the vector?
Within the vector.
Okay.
So that's why you see the binds. Whenever you see a bind, just think and. Whenever you see an M plus, or, right? These concepts map very cleanly to the nice sugar that we use. And so this is really what happens, right? We're going to bind the MTS. It's going to go into that function, and you can see M plus is going to do something strange, but we can see that it will bind that to unify to T and bind in the alternate branch to coffee. So M plus, again, looks very similar to bind. It takes an A infinity, and it takes a thunk, right? This is the thing that I haven't really explained yet. So what happens when you call M plus, because M plus is a polymorphic function, what happens when it gets a substitution as its first argument, right? Then it returns a choice, a type that we haven't seen, where it is the first field, and then it keeps the thunk in the second field. So right, cond E must produce a stream. That absolutely must be what's going on, right? In order to get multiple values, the moment you write cond E, it has to produce a stream, and it has to do something such that it forces the stream to the second goal. One of those is going to fail because we said in the second goal down here that Q has to be T. So the other ones can't work out. So choice looks like this. The rest of the stream is in the thunk. And where it gets crazy is that this guy, AN, could be any of those possible values. It could be nil. It could be a substitution, it could be a choice, or it could be a thunk itself. And this is when it's your mind starts going on a roller coaster ride, right? Because this means that streams can be combined, right? You could have a stream, and the stream could have a stream inside of it. So if you look at choice, this should look extremely familiar. Like, right? What happens when we call bind on a choice, which is a stream, right? We apply the goal to the head of the stream. Then we make a new thunk where we bind the goal to the tail of the stream. Right? You should have this. You should have this moment. You should have this moment. I stole this from Manuel Simoni, who's a character on Twitter, and he had this really funny GIF, and I had to use it. And the first thing you think, that's map. That is map, right? You take a stream, and you're going to apply the goal to each element in the stream, right? But wait. What happens if we call n plus on a choice, which was the crazy roller coaster ride thing that I was talking about? And if you look, what happens? We make a new choice. We don't do anything to its current value, but then we call an n plus on the other end, right? On the rest of the stream. And this should make you think of something different, which is mapcat, right? So calling n plus on a choice actually can take multiple streams and it flattens it out into a flat line, right? So at this point you feel like, I understand miniKanren. You know, you feel like you really wrapped your head around it. But there's some weird things are happening here. And where it gets weird is, okay, we do the n plus, but what's happening? Why is f, right? We have a choice. Why is f getting moved over in the thumb, right? We create an n plus, and for some reason, we are invoking the other function, right? And as you look through the miniKanren source or core.logic, you're going to see when n plus is involved, there's going to be this weird thing where we have a thunk, but we don't want to call that one. We want to call this other one, right? It's like sort of moving back and forth. And the reason it does this, and this is an advantage over Prolog, is here is a program, right, where we have a con e, and we have an evil goal. A goal, that first goal, is never going to produce an answer. It will never produce a substitution that we can use. But that kind of stinks because the second clause does. Right? There's a legitimate substitution waiting there to be used. Will, Dan, and Oleg came up with this cool idea. Was like, well, if we sort of like jump between branches, right? We can actually jump to the other side, and maybe there's something there that we can use, right? And that's exactly how this works. It's the flipping of the thunks that allows us to grab a substitution if it exists. And here's where it gets a little bit hairy. So this is the final case. What happens if we get a thunk? And you see that it does even more thunking. The interesting thing here is, again, we see the flipping. On this bottom line, if it's a thunk and we call n plus on a function, we simply invoke the other side and we put ourselves as the unrealized part of the stream. Inc is a bit strange. Fresh and conds are wrapped in this thing called inc. All goals are built upon fresh and cond. The inks prevent bad goals from stealing time from good ones that have results. That's what they're there for. Though this defies my understanding why we need them in this case, and it would be awesome to have a proof as to why do you need that in the previous slide. Like, why do those need to be there? It makes intuitive sense to me why you need them on fresh and cond, because every goal has to go through that, but it's not clear why you need them on thunks. So I'm almost done. This is the end. I mean, that's actually really all there is to how miniKanren works. Everything else is sort of like plumbing. Once we've started this process, we're going to get back the stream, and we call take star on it. All take star does is just run the trampoline. That's all that it really is, right? We're extracting something off the front, and we're calling the thunks, and we're getting more values, and calling the thunks, and so on. The trampoline extracts reified values out of the stream. Dan likes to refer to this as a distributed trampoline, right? The jumping back and forth. I'm just going to show the last bits of code so we can break down the macros. Run star is going to expand into a run false. We're going to splice them with goals. Run expands into a do all solve, and we splice in whether you put in false or a number of n, and the goals. Solve looks a bit like this. You can ignore the first part. Somebody submitted a patch where you can actually have multiple result bars if you want, just as a sugar. If you look at the bottom, right, what do? We create a fresh, we put the goals in there, we insert the reify goal, and we call that with FDS. We call take star. Because Clojure doesn't have tail call optimization, we actually use lazy sequences to prevent stack overflow. So that's why we call Clojure's take on the result of take star.
So, in Clojure, you're going to have backflow and no commas?
No,
It's the tilde.
it's a splice of the tilde.
Oh, okay.
So what's cool about miniKanren is there are no promises about the order, right? Once you understand that it's going to start going between different branches, miniKanren doesn't make any promises, core.logic does not either. miniKanren is a fundamentally concurrent design, and still to this day, nobody's really fully exploited it, which I think is sad. Though there has been some work, there's a branch called fork join now on GitHub, where Jim Dewey has done some work based on some monads, the continuation monad, where he actually is able to run goals in parallel, which is pretty cool.
We have 2 parallel implementations of miniKanren. They only run about twice as slow as the sequential.
Which is pretty good. It's not bad. So that's it. Hopefully some of that made sense. So do people have questions? I mean, cool. Thank you.
The current version of new operators is actually even shorter. It's closer to a page.
Cool.
But then now we're adding those operators we talked about today, and it's blowing up again.
Yeah.
The reifier especially got
It's bigger.
Did I mention that we talked today that when you get an output with reifying, if you have the same, if the conjuncts are all mixed up, that's okay, and you're always going to get the same answer, which is kind of a neat neat property, sort of like a church roster kind of property. Now, once you get into the cons, you don't know where you're going to go and how you're going to get there.
Yeah.
But for verifying what's actually going on, it's a really nice thing to have. And it wasn't trivial.
Yeah.
Any more than the underscore .0 was trivial. That was really not trivial at all. To get that to have that property that you could flip the arguments to equal.
It's cool. I mean, that's something that I don't do that much, but it makes perfect sense. Whenever you guys are like copying and pasting the results of miniKanren back into the REPL, it makes perfect sense.
The other nice thing about reifier is that in scheme, underscore .0 is a legal symbol, right? So you really can just like use it in. It's pretty sweet. The other thing I want to point out was Dan spent about a year working on Run.
Oh, wait a minute. Understating the truth.
How many years did you spend?
2.5 years trying to figure out that all we had to do was add that call to reify as a fake goal.
Yeah.
But it was part of the interesting things about solving hard problems, and I think it was a hard problem, is 95% of that time you think it's impossible. So you go into it a little bit and you play around, oh yeah, forget that. And then a month goes by, but it was a good 2.5 years from, I've got to get rid of that extra bar. There was an extra bar in the code, and it's in the first edition. Fresh uses var, and so did run in the past, and that was annoying because we kept on changing representations, and every time we did that, we had to change 2 pieces of code. That's really clumsy. So I said, I've got to get rid of this damn extra bar. And we were going to supper, my family, and something hit my head. I had no idea where it came from. I wasn't working on the problem. It just hit me. And I called up Will and I told him what I heard. And by the time I got done from dinner, we had it.
That's great.
Yeah, that was really the.
No, it's fun to stand on the shoulders of giants and to have them here. At Strange, totally. I mean, everything that I showed, it's in their books and in their dissertations and in their new papers. So hopefully this gives a model for a lot of people to not be afraid of the literature that they produced.
And then we've always felt, and when I say we, I mean myself, and Will feels the same way, but I've always felt that great ideas should be made as simple as possible. And therefore I use the simplest language I know. Maybe Clojure simple, I don't know. So that if someone wants to port it, it's true. I don't.
Is it true?
Anything away.
How long did it take you to do this? You only have to read it 8
It's easy to
times.
port once you understood it, right? It's relatively.
I will also say I don't envy anybody trying to do the system in a non-list.
It's a little trickier.
That sounds like a challenge.
There is a Python one out
There is a
there. Or maybe that's a list, but
No, it's a bit, no, it's strings. There's lots of strings in there. It's not so nice.
have you seen the Python?
I've seen a Python.
Okay. Yeah. When I first had it done, just on my comment, I had this graduate course, and I just said, okay, everybody pick one language. That's how easy I thought it was.
It was funny because I actually found a blog post from one of your students, and it was an undergrad class, and it was specifically said, Professor Friedman said we could pick any language, and he was really mad because we all picked what he likes to refer to as P languages. You had a question? Thank you.
I think you opened the door for a lot of people who know about OIC, and it's really awesome, and I really appreciate your work with us.
Thanks.
So, I guess, I don't know if I dismissed it, but how can miniFire or run or whatever does it do the part of those constraints on the variables?
Oh, so I mean constraints like beyond unification.
That you have core.0 is a symbol.
Oh, so yeah, I didn't talk about the constraints at all.
What do you mean?
There are no constraints in miniKanren.
Well, unification.
Well, yeah. Well, in your project, they have, said, we've got all these language terms, and they've got all these underscored ones and twos and stuff, and there's, oh, well, this one is a symbol.
Right, that's new stuff.
Yeah.
That's new stuff.
Or reifire is a little more
The
complicated.
only thing that's written is a draft. It's way
So
too
that's
drafted for
an
public
extension.
consumption. Yeah, that's an extension to this.
The one thing I will say, because miniKanren is so small, extensions are pretty easy. So I basically every paper they put out, I read, I'm like, I'm ready to implement this. And it's not hard because the system is very cleanly designed. And for example, when they say we have to change the reifier, that's great. You don't have to change the whole system. They just have to change how values are reified. And they have, basically they have like a constraint store, right? That they store different things in, and when they reify, they say, how is this constraint? And they simply print it, sort of construct it differently, the reified value. Other questions?
For starting to, if I wanted to go through this sort of process again and understand more where would I start to apply that book? Or
Yeah, I would start with the reason schemer. It's a great book. It's awesome. You can basically just print those things right into a scheme interpreter. It just works. You can download the code. It's 200 lines. You just load it up. Load mk.sem.
And you can get the TJ scheme for free.
Yeah, you can get the TJ scheme for free, which I highly recommend. That's how I did it. I actually learned how it worked by working through the scheme.
Yeah, I couldn't figure out how it works until I implemented it.
Which is why we can
Do you want to say anything about the cabling you're going to say? You don't have to go into any detail, but just like what it is and why it's important and why it might be worth using.
Totally. So Will did this really nice, very clean, also extremely hard to understand tabling implementation. Which is it's very awesome. And so what tabling is memoization for logic programs, right? So imagine you have a logic relation which does a graph, right? And the graph has cycles, right? If you want to find if two things are connected, the last thing you want to do is have a relation spin around, right? So if you have tabling, you can absolutely avoid that. Tabling will say, we've already seen this value before. We don't need to recur, the goal doesn't go into this crazy recursive loop. If you want anything more beyond that allows you to table, like, what's the other thing?
Well, basically, remember that everything can be a variable. So this graph that you're visualizing is visualized as a graph because you've got everything ground in your head right now.
Yes.
And when it's not ground, then it becomes the challenge.
Yes.
We'll have to deal with.
So that's something I didn't emphasize so much in my talk, is that miniKanren does really allow you as much as possible to reorder your goals. Things don't have to be ground, you can flip them, though that might be a subtle point, I think.
Does that tabling allow you to remove the reverse check?
I'm sorry?
Does that tabling allow you to remove the reverse check?
No. Yeah, I mean, tabling really is about that some relations can be very expensive, and you want some way to make your logic program more efficient. And it's a way to sort of cache things. But safe, as they said, it's important that it's safe. That if you don't have, if your logic bars are underground, it works properly. Cool. We have time for maybe one last question. If anybody has something else they want to ask. Otherwise, yeah?
I just wanted to get some insight into the thought process that goes into coming to the realization that a distributed trampoline is needed.
Well, where are you? We kept on trying different variations, doing different things. And one of the things we wanted to do is we wanted to flip the lines in the con. If you were at the talk today, you saw that we could flip the append lines. And we could flip anything. It's all flippable. So we wanted to figure out how to do that. And we read the reason schema, we acknowledged taking the code that had a lot of continuations and turning it into one-added code, basically. And it was all working just fine, except we'd come up with these examples. It didn't quite work. Going through instances because of starvation, various forms of starvation. So I sent it back to Nolen. It's not working. And he sent it back, and it worked. And then we tried some more examples, and more examples, and more examples, and discovered another one. And little by little, we ended up having to put these little inks, which are like random ills, on random places. And we all probably doesn't work. So that was the thing. I'm sorry.
It sounds like how I read my code.
What we wanted was something that could do the things we wanted to do. That was important. And we wanted to respect that history. So that we want to write macros in scheme to shorten, express it. You know, if you're trying to express and make it shorter and tighter, you can still do that. If you don't respect the macro, you're not going to do it. Or you're going to have all these quotes floating around or whatever. I mean, it's a mess. So the idea that you could use lexical scope to hold the logic variables, whatever, and that they would cover the entire space, it just made total sense to me. That's where it got started. We just wanted to comment. Somebody early on in the process said to me, well, why don't you just use syntax case there? Syntax case is this sledgehammer. And I said, well, I mean, it always makes things complicated somewhere along the way. It was going to sort of compromise. Well, you so much more optimal without having used the clever early things that you get out of it. So there's like a little mini lesson there. Don't just jump to where you want more control, but think really hard about it. And that way it paid off huge. I mean, you can show you an example of an expand of one of these binding expressions, bound star expressions, and you say, oh, that's all there is to it. And then one day, it became obvious that, wait a minute, they never take an arbitrary number of items, they just take some small finite number of items. And that just not having to have a list floating around. And remember, I relied on that. Who's the developer of this game. Ken did it, it's perfect. So all I have to do is kind of know what it's going to produce. So I would look at expand and see